Solving a first-order Bernoulli differential equation. So in solving a Bernoulli differential equation, we must first solve the given differential equation to reduce it to the standard form of the Bernoulli differential equation, which is dy over dx plus p of x times y is equal to f of x y to the n. So after expressing it to the standard form, we can determine now the u, which is equal to y to the 1 minus n, and taking the first derivative of this equation, we can get du over dx is equal to 1 minus n y to the negative n dy over dx. So we can use these two equations to replace all the y's in the equation in terms of u, and replace dy dx in terms of du over dx and u. So after replacing that, the equation will be transformed from being nonlinear to linear differential equation, and after getting the linear differential equation form, we can use integrating factor to solve for the function. So solve the differential equation xy squared y prime minus y cubed is equal to x squared. So we can rewrite this y prime as dy dx, so the equation now becomes xy squared dy over dx minus y cubed is equal to x squared. So we wanted to equate this whole equation by dy dx. So what we will do is to transfer first this y cubed to the other side, so the equation becomes like this. It becomes positive y cubed, and then we wanted dy dx to have a variable of 1, so the whole equation will be divided by xy squared like this, and so this xy squared will just be cancelled out. So what's left in the left side of the equation is dy dx, or looks like this: dy over dx is equal to x over y squared plus y over x. So if we transfer this y over x to the left side, it becomes like this. So it can be noticed that this form is in the standard form of the Bernoulli equation. So taking this to the next slide, so we arrive at this equation, which is the standard form of the Bernoulli equation. So from here, we can determine the value of n, which is n is equal to -2 from the exponent of y, which is -2. So we can also determine the value of u, given that u is equal to y to the 1 minus n, or just equal to 1 y plus 2, or u is equal to y cubed. So the value of y we can also get in terms of u is u to the 1/3, and taking the first derivative, we can get dy over dx, which is equal to 1/3 u to the -2/3 du dx. So we can use these equations to replace here in our Bernoulli's standard form. So before substituting, we first transfer this y over x to the other side, so the equation becomes dy over dx is equal to x y to the -2 plus y over x. And then knowing that dy dx is also equal to 1/3 u to the -2/3 du dx, we can use this value to replace here, and variable y by this equation. So what will happen is that dy dx will be transformed into this, and x to the xy to the -2 is just equal to x over y squared. So x here over square of this, which is u to the 2/3, plus y, which is u to the 1/3 over x. So we wanted du dx to be to have a variable of 1, so what we'll do is multiply this whole equation with this, So if you multiply that with 3u to the 2/3, this equation will this expression will just cancel out, leaving as du dx. So the equation will be like this. So it will cancel out. And then here we have 3x to the u to the third. Then these are same variables, so it just cancel out. This will just cancel out, plus 3u to the 1/3 times u to the 2/3. So 1/3 plus 2/3 is just equal to 1. So this expression just is equal to 3u. So we can just cancel out this one. Is equal to 1 over x. So the equation is now du over dx is equal to 3x plus 3u over x. So if we transfer this expression to the other side, it will look like this: du over dx minus 3 over x times u equals to 3x, which is a linear differential equation. So taking this to the next slide, we have here du dx minus 3 over x du equals to 3x. So this is a linear differential equation. So we can solve this function by using an integrating factor, which is represented by v. So the integrating factor will be v is equal to e to the negative integral of 3 over x dx. This 3 over x is from here. So integrating this part, we have v to the e to the negative 3 ln of x, which is just equal to e to the ln x to the negative 3. Then e and ln will just cancel out. So what's left now is e to the x negative 3. So if we multiply this integrating factor, the whole equation, what will happen is that the derivative of the left side times the integrating factor is just the derivative of u times x to the negative 3 is equal to 3x times the integrating factor x negative 3. So we can rewrite this by like this, and we can see that 3x over x cubed, our variable x will just cancel out. This becomes x squared. So integrating both sides here dx. So this part will just cancel out. So what will happen, the equation will become like this: negative 3 over x plus constant. So we wanted this equation to be equated by u, so we can divide this whole equation by x to the negative 3, or what will happen in the equation is that it will be equal to u is equal to 3x squared plus cx cubed. Then recalling that our u is just equal to y cubed, we can replace this u by y cubed. So the equation now will be y cubed is equal to 3x squared plus cx cubed. So this is our final solution. So in this video, we will try to solve a problem about applications of first order differential equations. The problem is the inner and outer surfaces of a hollow sphere are maintained at temperatures T0 and T1, where the inner and outer radii of the sphere is RO and R1, and the thermal conductivity is also given, which is K. So the questions are: find the amount of heat lost from the sphere per unit time, and what is the temperature distribution through the shell. So the problem looks like this. We have a spherical shell which is hollow inside, and the inner radius is r sub o and the outer radius is r sub 1. temperatures T0 for the inner temperature and T1 for the outer temperature. Thermal conductivity is given as K. So the first question is how much amount of heat loss from the sphere per unit time. So in solving for this question, we will be using the Fourier's law of conduction, which is defined by the equation Q sub R is equal to negative Ka dt over dr, where Q here is the amount of heat loss per unit time. So we can see that this equation is a separable equation, so we can transpose dr and a to the other side, making our equation like this. So a here is the area of our sphere, where area is equal to 4 pi r squared, so we can just replace a with this value or this equation. So our equation now becomes qr over 4 pi r squared dr equals negative k dt. So this equation we can now integrate. So we have arrived with this equation. Now we will try to integrate it by establishing limits. So become like this. So for our radius, our limits is from the inner radius to the outer radius, while for the temperature is also from the inner temperature to the outer temperature. So integrating this equation, we will have this form. So we can notice that both sides carry negative side, and if we distribute this negative side to the variables inside the quantity, our equation now becomes like this. So we wanted to equate this whole equation by QR, so we'll just have to transpose these quantities, including the 4 pi, to the other side. So our final equation now becomes this one. This is our formula for finding the amount of heat lost from the sphere per unit time. For the second question, which is the temperature distribution through the shell, we will be using the heat equation for steady state condition and no heat generation, which is in the form of this equation. So by double integrating this equation, we can have the formula for temperature or T. So double integrating, we will have this equation. So we can see that we have two constants here, C1 and C2. So before establishing the equation for T, we need first to find an equation that defines C1 and C2. We can find that equations by knowing the temperature at RO and R1. So at RO, the temperature is TO, or the temperature at the inner radius of the sphere. So substituting this value to our equation, we can have this TO is equal to C1 over RO plus C2. Then the temperature at the outer shell is also known as T1. So again, by substituting this value to the equation here, we can have this equation. So these equations, we will use this for determining the equation that will define C1 and C2. So we have established this. So next we will be equating this equation by C2, and the other side C2. So we can see that these equations are all equal to C2. So this expression and this expression, we can just equate this to each other, this part. From this equation, we can now derive an equation that will define C1. So by manipulating this equation, we can get the equation for C1, which is this equation. And using this equation to get C2, so we will use this expression, substitute it here in C1, we will have the equation for C2, which is in this form. So let us remember that our equation for temperature, as we have arrived earlier, is in this form. So by plugging in the values of C1 and C2 here, we can have the final equation for the temperature distribution, which is in this form. So this will be the equation for the temperature distribution through the shell. Solving a first order linear differential equation. So in solving a linear differential equation, we must first express the given differential equation into the standard form of linear differential equation, which is dy over dx plus p of x times y is equal to f of x. After expressing it to the standard form, we can now find the integrating factor given by v is equal to e integral of p of x dx. After that, we can multiply this integrating factor to the differential equation. Then, after that, we can now integrate both sides. And please remember that the left side of the equation is just the derivative of the product of the integrating factor and the variable y. We can see more of this in the problem that we are going to solve. So, find the general solution of the equation y prime plus 2xy plus x is equal to e to the negative x squared. So we can rewrite this y prime as dy over dx plus 2xy plus x equals to e to the x squared. So since we wanted to form this equation into the standard form, we first transpose this x. We transpose this x to the other side. So it becomes dy over dx plus 2xy is equal to e to the negative x squared minus x. So as we can see here, this form follows the form dy over dx plus p of x times y is equal to f of x, which is the standard form for the linear equation. So therefore, this form of the equation is now in the standard form of linear differential equation. So next, we already arrive at this equation. So next is we find the integrating factor. So in finding the integrating factor, we use v is equal to e integral of p of x dx, where our p of x dx is just 2x. So the equation becomes this one. V is equal to e integral of 2x dx. So integrating this part, we get e to the x squared. So now we have our integrating factor. This integrating factor will be multiplied to this equation. So we multiply this integrating factor to this equation. This equation will multiply like that, and then so the equation becomes like this. So as I have said earlier, the left side of the equation is just the product of the integrating factor and the variable y and its derivative. So the derivative of y times e to the x squared, this is the left side, this represents this, is equal to e x squared times e x squared minus x e to the x squared. So as we can see, this part of the equation will just cancel out, since negative x squared minus x squared is equal to 0. So this part will become 1 minus x to the x squared. So the equation now becomes derivative of y times e to the x squared equals 1 minus x e to the x squared. So let's take this to the next slide. So we arrive at this equation. Next part will be integrating this equation. So if we integrate the both sides, let's put here dx. So as we can see, this part will just cancel out, so leaving us with y to e to the x squared, and the derivative, the integral of 1 dx is just x. So the equation becomes like this, minus the integral of x e to the x squared dx. We cannot directly integrate this, we use let u. We let u is equal to x squared, and then we get du, which is 2x dx, or 1/2 du is equals to x dx. So now we can integrate this part, and this becomes ye to the x squared is equal to x minus 1/2 e to the x squared plus constant. So we wanted to express this equation. We wanted to express the equation in, or equate this equation by y. So we will divide this whole equation by this e to the x squared. So it becomes like this, and this part will just cancel out, and also this part. So we are left with 1/2 there. So for rewriting this equation, it becomes y equals to xe to the x squared plus ce minus x squared minus 1/2. So this is the final equation. Sample problem for a first order differential equation using separation of variables. So the problem is, show that the change of dependent variable from y to v defined by the substitution v equals ax plus by plus c will always transform the equation y prime equals f of ax plus by plus c into a separable equation where a, b, and c are all constants. So let's first take into consideration this equation. So v ax plus by plus c, if we get the derivative of this, we can get dv over dx equals a plus b dy over dx. So if we transform this a to the other side, we can have b dy over dx equals dv over dx minus a. So we wanted to have this dy dx to have a variable of 1, so we can multiply this whole equation by 1 over b, so that this side will have a variable of 1. So multiplying by 1 over b, so the equation will now become dy over dx is equal to 1 over b dv over dx minus 1 over b. So this equation is now very important since it is equated by dy over dx. So let's take this to the next slide. So we already got this equation, and knowing that y prime is equal to f of ax plus by plus c, and we can also rewrite this in the form of dy over dx is equal to f ax plus b plus c. Then knowing that this dy dx is equal to these terms, so we can write this as like this, and knowing that ax plus by plus c is equal to v, so we can substitute these whole terms as v. So the equation becomes 1 over 1 dv over b dx minus a over b equals v. So by transposing these terms to the other side, we can have this. So we wanted to separate the variables, so we wanted to have v on the left side and x on the other side. So we will multiply this whole equation by dx, so that dx will be transferred in the right side of the equation. So this will become like this, dv over b is equal to v plus a over b dx. So since we wanted to separate variables, so we wanted all v's to be in the left side and all x in the right side, and these terms don't have x but does have v, so we will transfer this in the other side. You can see it in the next slide. So we have here, so by transferring this equation to the left side, we will have dv over b times v plus a over b equals dx, or can be written as like this, and as we can see, all of v are in the left side, and since since we don't have any x variable, so 1 dx in the right side, and this is in the form of n of v dv is equal to m of x dx, which is the form for a separable equation. So therefore, the change of variable from y to v defined by the substitution v is equal to ax plus by plus c will always transform the equation y prime is equal to f of ax plus by plus c into a separable equation.